Okay, so let me start this video. First, let's see the contents. First, I will explain some theoretical background containing the noise model, and then I will explain the wavelet transform based denoising scheme, and then I will show you that use of waveletAnalyzer tool by which you can do the denoising of images. And then I will explain the two important MATLAB functions, wdencmp and ddencmp, which will be used in the denoising. And then I will use a newer function which is the wdenoise2 with example code. So let's start. First, I recommend you to watch my these previous two videos. This one, first one is about the wavelet transform theory and its applications. It explains about the wavelet transform theory, filter bank theory, and various wavelet types and their applications. The link is given in the description. And then second one is about denoising, but it is denoising of the one-dimensional signal. I mean signal like audio signals. So these two will be very helpful for you to understand this video. These two links are given in the descriptions. Now let's see some theoretical background. When a signal is transmitted over some distance, it is frequently contaminated by the noise, and the simplest noise model is given by this equation. Here fxy is my original signal or image, and nxy is a noise, and f-xy is my corrupted or contaminated signal. The basic assumptions for the noise signal nxy for the proposed scheme are that it is additive in nature, and it is white Gaussian noise with a zero mean value, and it's of high frequency signal. So our objective here is to remove this noise nxy from image f-xy using wavelet technique. And this is the wavelet based denoising scheme. Here you can see that the input signal fk or image is first decomposed into various wavelet coefficients using discrete wavelet transform. These wavelet coefficients, I mean particularly the detail coefficients, only are thresholded, and then these thresholded coefficients are collected together, and by using the inverse discrete wavelet transform we get our denoised image back. Okay, now how to find these threshold levels? To find the threshold levels, we have various methods such as the universal threshold method, which is also known as a visual shrink or square root log, and the Bayes method. We have the Shore method and min-maxi, etc. We have FDR also. And how the thresholding is done? The thresholding is done mainly by these two types. One is called the hard thresholding, and second is known as the soft thresholding. In the hard thresholding, suppose my threshold values are minus lambda and plus lambda, then all the wavelet coefficients lying in this range minus lambda and plus lambda are neglected, they are zeroed out, while the other coefficients remain unchanged in hard threshold. While in soft threshold, all the wavelet coefficients lying in this range minus lambda to plus lambda, they are zeroed out, but the coefficients beyond this range are also degraded by a constant, as you can see here. And now let's see the MATLAB's waveletAnalyzer tool that can be used for denoising. So when you execute on command prompt this waveletAnalyzer, you will get this window, and in this window just locate where is the two-dimensional. So this is two-dimensional, and wavelet 2D, just press this wavelet 2D button. So you will get a window where you can choose your image, and then you can do the denoising. So let's see this in MATLAB. So let me jump to the MATLAB. So let me type this waveletAnalyzer in command prompt, pressing enter, you get this window, and then locate two-dimensional. So by pressing this wavelet 2D, I get this window. Here go to the file, load image, and here you can load your image. For example, this is a noisy image of Lena. Open it. This image is loaded, which is noisy, you can see. And now choose your wavelet. For example, I am choosing the orthogonal 2.2, and the wavelet decomposition level is 2. So just press this analyze. So the wavelet decomposition is done for this noisy image. Now here, out of these 4 buttons, you can see that fourth one is of denoise. So when you press this button denoise, the another window opens. So here you can see your noisy image, and these are your wavelet coefficients, all detail coefficients at level 1. So at the level 1 you can see this is horizontal coefficient, these are diagonal coefficients, and these are vertical coefficients, and at level 2 these are horizontal, diagonal, and vertical. Now let me choose the threshold. So you can choose soft threshold or hard threshold, and my image noise is actually the scaled white noise. So the threshold estimated for level 1 and level 2, you can see here. The level 1 threshold is 80.3 and level 2 threshold is 75.11. So these are threshold levels you can see in this window. And I'll just press this denoise button, you will get your output. So this is your denoise image. You can see really a good result. Here you can see lots of background noise, and here it is reduced up to a great extent. So this is how you can use this Wavelet Analyzer tool. You can import any of your image, and you can choose any of the wavelet, and you can see their corresponding effects. So let me close it. Now let me jump to my presentation back. Okay, so now let's see the 2 important functions, MATLAB functions, which will be used in denoising. So this is first is the wdencmp. This function is found in all older versions of MATLAB, and it can be used for denoising for both 1D as well as 2-dimensional signals. So you can use it for audio as well as images. And this is the basic syntax. Here the image, this is your input noisy image, and this is your output denoised image. And W name is the name of the wavelet which you will use. N is the number of decomposition labels, and GBL or LVD, you can see here. Either you will write GBL only or you will write LVD. So when you write GBL, that means there will be a single global threshold, and if you write LVD, that means it will be a label dependent threshold. Okay, and now THR is obviously the threshold value. When you write GBL, obviously there will be a single threshold value, and if you write LVD, there will be the 3 by n matrix. So THR, you have to define a 3 by n matrix. So what is 3 by n matrix? 3 actually are rows, n are number of columns. So n is your decomposition level. Mind this. So if you write 2 here, that means 2 level of decomposition, that means it will be a 3 by 2 matrix, and each row corresponds to horizontal, diagonal, and vertical detail coefficients, while n represents number of decomposition labels. That means it includes all the threshold values for each horizontal, diagonal, and vertical coefficients, and for each level. S or H. S or H is the type of thresholding. Either you will write S or H, that's corresponding to the soft and hard thresholding. Now keep app is either 0 or 1. If you write 1, it means the approximation coefficient will remain unchanged. Only the diagonal coefficients will be thresholded. There will be no thresholding of approximation coefficients. Otherwise, they can be thresholded. Now, let's see the use of ddencmp. The question is that in the previous function, how to get these values, the THR, SOH and keypap. These you will get automatically from this function ddencmp. So you can see that when you pass your input noisy image img and you define this den for denoising and wv for wavelet. So then executing this ddencmp, you will get all these three values: THR, that means the threshold value, and S or H corresponding to soft and hard thresholding, and keypap, whether the approximation coefficient should be thresholded or not. So this is the basic syntax, and these are the explanation of these attributes. So let me show you its example code, but before it, that how it computes the threshold. Actually, this threshold is computed on the basis of this universal threshold method, which is also known as the square root log method, which was given by the Denoising, and this is given as the sigma j, that is the noise variance, square root 2 log n j at the jth level, and is the length of wavelet coefficients, detail coefficients. So this I have explained in detail in my previous videos of one-dimensional denoising. You can refer that. And now let's see the example code which will use this wdencmp and ddencmp. So first, when this line is executed, UI get file, a system dialog box will appear to choose your grayscale image. You can select your image. Then your image will be read by this imread function. So whole image pixel values will be accommodated by this img variable. This is a noiseless image, original image. So first I am adding some noise to this image to make it noisy. So im noise function is executed. This is your original image, and Gaussian noise is added of 0 mean value, and the variance noise variance is 0.05. And we need to define the signal extension mode, DWT mode, which is a periodic extension of the signals to treat the boundary problems. And now execute first ddencmp function. So when you execute ddencmp, you will get the threshold and SOH and keypap values that will be used in wdencmp. So den is defined for denoising, and wv defined for wavelet, and img, and this is my noisy image, this one. Okay, so I get all these threshold values, etc. So once these values are known, I can pass these values here in wdencmp. So now wdencmp needs these values. So you can see the THR, SOH and keypap. And this is the GBL. The GBL means I am using a single global threshold here. I am not using the LVD, that means the level dependent threshold. And this is your noisy image, and simlat 4 is used for decomposition, that's a wavelet, and 2 is the number of decomposition level. So wdencmp when executed, you get this output, which is your denoised image, right? And I have written the code for label dependent also. So if you write LVD in place of GBL, then your THR will be should be a 3/n matrix. Since I am using 2 decomposition labels, so it is a 3/2. So it is a 3/2 matrix. So you can see that it's a 3/2 matrix. So here you get THR, 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 THR and THR. So each row corresponding to horizontal, detail and vertical. So this is for level 1 and this is for level 2. And these are the plotting commands, and this is for finding the SNR, signal to noise ratio. So you can see that what is the improvement after denoising. So first is actually the original image versus noisy image, and the second one is the original image versus denoised image. So you can see that is there any improvement in the SNR after denoising or not. So let me jump to MATLAB to see this code execution. So this code I have already written. So let me press this run button. So the system dialog box appears and it asks me to choose my image. So let me I choose the paper image, open, and this is the output which I'm carrying. So this is my original image and this is the noise image. You can see lots of noise in the image, and this is the denoise image. It's quite good one. And let me see the SNR values, what SNR I'm getting. Yes, so you can see that original versus noisy is 17.39, while the original versus denoise is 22.3638 dB. So obviously there is a improvement from 17 to 22. So denoising is working. So let me jump to my presentation. Now let me come to a newer version of MATLAB function, which is wdenoise2. This function was introduced in version MATLAB 2019A. So you won't be able to execute this in the versions prior to this 2019A. This has more control actually and more refined, and this is the syntax you can see. So imgdn is your output and this is your input noisy image img. N is your number of decomposition level. Wavelet, here w name, that is the wavelet name you will define. That means dB, har, or bi-orthogonal coefficient, etc. And then denoising method, in place of this method you will write denoising method. So what denoising method we have? So we have here various method like base, which is the default. If you don't write it, the base will be taken. We have FDR, minimax, sure, and universal threshold, right? Such flexibility was not there in the previous wdencmp function that used only the universal threshold to estimate the noise variance. But we have here these 5 functions, five methods, and the noise estimate here in place of li or ld you will write either level independent or level dependent. So that is similar to your gbl and lvd of the previous function. That means level independent means a single threshold will be used, and for level dependent there will be different sigma for each level. And then noise direction and the matrix, it will be a matrix like this. This is for example, the default is HVND, all horizontal, vertical, and diagonal wavelet subbands. Here you need to define these because that how to choose how to find the noise variance sigma on the basis of what detail coefficients. I mean, can we use all the 3, or you can use any one or any 2 out of these 3. Okay. And then the threshold rule, th threshold type. So you have the hard, soft, mean, and median threshold. Actually, depending on the methods used, these methods, denoising method, we need to choose these thresholding type. So if you choose minimax, sure, and universal threshold, then you need to choose only hard and soft, right? If you choose base, then you can choose either median or mean or median. The default is median. And if you choose FDR, then only the hard is option, right? So these methods actually define what type of thresholding you choose. So for most of the methods, the soft is the default. So let me show you one example code that will use this wdenoise2 function. Okay, but before it, there are two more attributes in this function. One is the cycle spinning and other is the color space. So for simplicity, I have omitted these two, but you can also use them. Cycle spinning is used for SNR improvement. Actually, this is the circular shift. The default is 0, that means there is no circular shift. If you write, for example, here some non-negative integer like 1, 2 and 3, there will be a circular shift along the rows and column of the images of the image, and the image will be thresholded, and then at the last the average will be taken of all those versions to get the final image. It is seen that by doing this circular shift, there is a slight improvement in SNR. So for some shifting, there is an improvement, but after that it becomes constant. So you need to try that up to what number of cycles spinning you get improvement in SNR. Okay, so obviously by doing so circular shift, there is a lot of computation is required, so generally we omit it. And then the last one is the color space. This color space is used only for color images. If you are denoising the color images, then you can use it. If you choose the PC as the default, that means your color image is first projected to the PCA space, it is denoised there, and then it is returned back to the original color space. But if you write original here, then there is no projection to the PCA space. Okay, so let me show you one example code. Here you can see that first UI get file is executed. You can choose your your image, your IM read, that means your image will be read and whole image pixels will go into this img variable. And since this image is noiseless, so I'm adding the image noise using IM noise. So we are adding the Gaussian noise of 0 mean value and the noise variance is 0.05. So IMGN is my noisy image, and then I'm calling this function wdenoise2. So this is my noisy image. This is my wavelet decomposition level n, and the wavelet used here is the Q5. Noise estimation method is the label dependent, and the denoising method is base, and the thresholding rule is median. Obviously that is default for base. Even if I don't write these two, the base and median will be taken as a default, and the noise direction is HVD. That means this is also a default. Okay, and these are some plotting commands. So I am plotting the original image, noisy image, as well as the denoise image, and these are commands for finding the SNR as we have seen earlier. So this SNR is original versus noisy, and this SNR original versus denoise. So let's see whether there is a improvement in the SNR or not. So let me jump to the MATLAB. So this program I have already written. You can see by pressing this run button I can execute it. Okay, this is the output. You can see this is the original image, this is the noisy image, and this is the denoised image. So let's see what happened to the SNR. So yes, you can see that the previous SNR is 17.37. That is between the original versus noisy, and the SNR between original and denoise is 24 dB. So you can compare these two values with the previous output. So we got 22.36 in the wdencmp, but in this I got 24. So that is 2 more dB I got in this example. Even it can be improved by a little bit more tuning this example. So let me close it. So let me jump to the presentation. Okay, that's it for this video. Hope you liked it. Thank you.